Вот я начинаю говорить, и что, меня слышно? Can you hear me? Да? Ну, прекрасно. Okay. So as I promised, all the hard work was done, and now we only derive some pleasant applications. So the first application is proposition 6, that, as I said last time, the Steinberg module is irreducible and self-dual. And by the way, last time you weren't here, so I spoke Russian, and were you able to catch up? No. And then I wonder how you can catch up today, but okay. So anyway, we proved last time that that everything is compatibly Frobenius split. Absolutely everything. I mean, de Mazur resolution, flag variety, parabolic flag variety, all the de Mazur sub-resolutions, all the Schubert sub-varieties, everything is split simultaneously. And this Steinberg representation was just the global sections of some particular dominant line bundle, like this. And well, it's self-dual, so it's also isomorphic to so-called V of P minus 1 rho with while module. So it's both while and dual while. Okay. The proof is very short. We know for a long time now that all the possible splittings, and we know that they exist in this case, they live in the global sections of the P minus 1 first power of the anti-canonical line bundle. We know from here there is the evaluation morphism to, say, global sections of the structure sheaf. There are just constants. Okay, but what we also established last time is that there is the multiplication of morphism from the tensor square of the Steinberg module to this thing. Now it's isomorphic, there is evaluation, so in other words, there is a pairing. We obtain pairing like this, say chi. And we know that chi, well, the pairing chi is non-degenerate. Since the splitting in question was obtained as the product of the highest weight vector and the lowest weight vector in here. We proved this last time, and by the construction, F plus generates the Steinberg module. Okay, well, maybe I should say that F plus tensor F minus generates the tensor square. Okay, so this way, well, maybe at least at this point, maybe we know that that at least that this is not zero, because this is not zero. this is the splitting here, and it goes to 1, so it's not 0. So we obtain a non-zero map from Steinberg to the Steinberg dual. Okay, and now because of this, we know that well, I don't know where it's zeta. Zeta of f plus is not 0, but on the other hand, we know that f plus does generate the Steinberg module, so this map must be surjective and isomorphism. Okay, and that's it. Now, why is it irreducible? Just because of the same thing, because it is generated by f plus, and if it were not irreducible, because of this non-degenerate pairing, the component containing f plus would split off, but we know that f plus generates everything. Okay, so this is proved. And another corollary is theorem 8 that I promised many times long ago, that for any dominant lambda, dominant weight lambda, the corresponding line bundle on the flag variety does not have higher cohomology, and for some reason it has number 8 in my notes. And yeah, because previous theorem 7 was that exactly that this guy defines a splitting of the flag variety compatible with all the positive Schubert divisors and all the negative Schubert divisors. Okay, so given a dominant weight, we obtain the line bundle L of lambda on the flag variety, but sometimes, so for some lambda, that yes, that is the lattice of characters, so it's sort of dual. Well, you can also have this asterisk as the lower index, and then it means co-characters, so homomorphism from multiplicative group to T, and characters is homomorphism from T to the multiplicative group. So for some lambdas which are not regular, this L of lambda is the pullback of line bundle, say P, from the partial flag variety. Okay, there is a morphism from complete flag variety to a partial parabolic flag variety, and sometimes the line bundle descends. For example, if lambda is 0, then we have just the structure sheaf, and suddenly this structure sheaf descends from the structure sheaf of just the point G mod G. And there are some intermediate cases. So we have such line bundles on the parabolic flag varieties. And what I want to say that, first of all, the higher cohomology of any Schubert variety in this parabolic flag variety with coefficients in this line bundle restricted to the Schubert subvariety vanish because of the Frobenius splitting. Yeah, at the very first class about Frobenius splitting, we had such a consequence in general. Just I say that some line bundles on the full flag variety are lifted from well, appropriate line bundles on the parabolic flag varieties, and then this is the notation for this line bundle on the parabolic flag variety. Okay, so this is so, and also the restriction homomorphism from global sections on the full parabolic, well, sorry, on the parabolic flag variety with coefficients in this is mapped surjectively onto global sections of any Schubert variety with coefficients in this line bundle. Okay. So once again, these are the direct consequences of Frobenius splitting, and we will use them from now on. And now we introduce new, very important notion that a morphism f from x to y, say proper, projective, is called rational if the complete total direct image of the structure sheaf of x is the structure sheaf of y. That is, the zeros, well, usual direct image is just the structure sheaf of y, and all the higher direct images vanish at all. Okay. So now we have an evident lemma 6 that says if S is a locally free sheaf on Y, then the natural map from its cohomology to the cohomology of its pullback to X is an isomorphism, and it's just projection formula. And also it says that if we have a composition of two rational morphisms, then it is rational as well. G composed with F is rational. Just because the direct image of composition is composition of direct images. Okay, so this is, yes. Yes. Well, if you want to compute it somehow degree-wise, you will have a spectral sequence, but it will, well, give the same conclusion. But you can just compose derived functors at the level of derived categories, and it's more invariant way to say what you say. Okay. What exactly? What's the question? No, we will have some linear spectral sequence right now, so. I just say that the composition of full direct images is the full direct image of compositions. So at the level of derived categories, well, the same thing is true as for usual non-derived compositions. That direct image of composition is composition of direct images. Okay, so the next lemma is less trivial and much more, well, very important, because we will see later on today that this notion is pretty useful, and in fact it rarely happens. Well, for example, if y is if y is any, say, singular variety and x is non-singular, then this property does not depend on x and f. It is some inner property of y. If it happens to be true for say, for one resolution of singularities, then it's true for any other resolution of singularities. So it's some internal property of y. But it is a rare property. Most singularities are not rational. But all the Schubert varieties singularities will turn out to be rational, and we will see how it works, why it is so, and how it is used. But it is hard to check this property. And somehow you see that this property is sort of local. Yeah, you check it, well, in the neighborhoods of points of y. But in case when y is proper itself, then there is some global way to check this property. And this is lemma 7. So it's some strange direction, unexpected. So we, in our class of algebraic geometry, we have seen dozens of applications of local to global principle. Yeah, we proved some global statements by local considerations, and that's their natural approach. But in this case, it's exactly opposite. We will prove some local statement from the global considerations. So it's an unexpected global to local direction. Okay, so what is this lemma about? So first of all, we have L, an ample line bundle on Y. And then if the higher cohomology of the pullbacks of powers of this line bundle vanish for high enough powers, then it guarantees that the higher direct images of the structure sheaf, structure sheaf of X are all zero. That's good. That's part of this claim. Yeah, all the higher direct images vanish, and the zero direct image is just the structure sheaf. So the second part is about the zero direct image. So if F is surjective or dominant, and the global sections of high enough powers of this ample line bundle are isomorphic to global sections of its pullback on X for high enough powers, then this the push forward of OX is just OY. Okay, so if we know these two claims, then the morphism F is rational. Yeah, it's here. Well, I don't know. It's isomorphic to zeroth global sections on X. Okay, so the proof uses the Leray spectral sequence, as you suggested. So we the second page is the pth cohomology of x, of y with coefficients in Q direct image of push forward of the pullback of L to the power n. And so it will converge to the P plus Q cohomology of x with coefficients in the pullback of L to the power n. Okay. And by the projection formula, we know that this is the same as pth cohomology of y with coefficients in the Q push forward of the structure sheaf or x tensored by L to the power n. Okay, and then we know that L is ample, so for high enough power, this and P positive, this will vanish. Okay, so it implies that the qth cohomology of x with coefficients in the pullback of L to the power n equals just the zeroth cohomology global sections of y with coefficients in the qth direct image of OX tensor L to the power n. Okay, for n big enough, but just by our assumption, this vanishes. Well, maybe not this. Maybe that vanishes by our assumption. Okay, and hence this vanishes. But now we know that this higher direct image is a coherent sheaf. Okay, and so it must be generated by its global sections after high enough twist. But there's no global sections, so it must be 0. Is generated by its global sections for big enough n, but the global sections vanish, so the sheaf vanishes itself. Okay, we proved A. Yeah, because for it does not vanish for q equals 0. Okay. And now the next step is exactly q equals 0. So let's consider the natural morphism from OY to the push forward of OX. It's an embedding, certainly. So in principle, there may be some quotient Q, but we want to prove that Q vanishes. Okay. To this end, we twist everything by L to the power n, again for high power n. And then we obtain from this short exact sequence, the long exact cohomology sequence. 0 goes to global sections of y, but we twist with L to the power n. Then it goes to the global sections of this push forward by projection formula. This is just cohomology of the pullback of L to the power n. Then it goes to the cohomology of y with coefficients q tensor L to the power n. Then we repeat, it goes to h1 of y with coefficients L to the power n, and so on. But when n is high enough, this vanishes. And this is an isomorphism by assumption. And so it means that the global sections of the twist vanish. But again, by the same reasoning, for high enough n, this coherent sheaf is generated by global sections, so it vanishes. And hence, Q itself vanishes. Yeah. Okay, so we proved this lemma, and now we'll apply it. But I find this lemma very, very elegant. Unfortunately, maybe I'll raise its proof rather than formulation. Okay, so the next theorem is rather innocently looking, that any Schubert variety is normal. But as I mentioned probably last time, it's really an important and difficult point. So in the original work of de Mazur, where he introduced his resolutions, he proved everything except this. So he somehow missed this point, and then somebody found out that this is missing, and it was a real big problem for many years, till some Indian mathematicians resolved it using Frobenius splitting. That any local ring is integrally closed. Okay, so as I argued before, the Schubert varieties in partial flag varieties, parabolic partial flag varieties, are sort of equisingular to the flag varieties, to the Schubert varieties in the full flag variety, and hence it implies that any parabolic Schubert variety is normal. For any W. Okay. And somehow the proof will use certain induction when we'll go to parabolic flag varieties and then back to the full flag varieties. Okay. So we choose a simple reflection. Si, S such that Ws is smaller than W. I mean, shorter than W. The length here is smaller than the length of W. Okay, and consider the subminimal parabolic pi. Well, that corresponds to this Si, this ith place, say negative alpha I, and this is my parabolic subminimum. So the quotient pi modulo b is just isomorphic to p1. And it implies that the projection from the full flag variety to G mod p I has fibers p1. It's just a p1 fibration. Okay, we'll call this fibration pi. So then we know that under this assumption, if we restrict this fibration pi to our Schubert variety xw, then the image is well, the corresponding Schubert variety in the partial flag variety xp, and well, this is also called pi maybe, and this is just also p1 fibration. So somehow the most simple but somehow representative case to think about is just SL2. The flag variety is just P1, and it corresponds to S, the only non-trivial element of the while group. And the partial flag variety will be just a point. So there are two things. There is X, the unit element, this is just a point. And the whole thing is just XS. And well, we know that SS is E, and it's smaller than S. And so the whole thing projects to the partial flag variety with a fiber P1. But if I take the Schubert variety XWS, the smaller thing, it will project to the same image in the partial flag variety, but birationally. Okay. So, well, if I take pi restricted to XWS, from XWS to here, it will be birational. Namely, all the Schubert varieties are the unions of cells, and on the open cells it will be just an isomorphism. But on the boundary it will contract something else. There's no boundary in this case, but in general, away from the maximal cell, it will be some, well, it will have no trivial fibers. Okay, and now we will play with the combination of two. Namely, we will prove this normality statement by induction. Induction in length of W. We may assume that XWS is normal, and we want to prove that XW is normal. Okay, but since this is P1 fibration, they are equisingular, and the normality of XW is equivalent to the normality of this parabolic version. So we want to prove the normality of the parabolic version, and namely by the main Zariski theorem. We need to check that the direct image, well, maybe let me call it, I don't know, pi bar to distinguish from some other pi, direct image of the structure sheaf of x, w, S equals the structure sheaf of X WP. We know that this is normal by induction. The map is birational, and we only need to check that the structure sheaf goes to the structure sheaf. So this is what we have to check. Okay. So let's check this. Now we will check this using this elegant lemma 7. So for any dominant lambda, but such dominant lambda that the corresponding line bundle descends to the partial flag variety. So let me call it the character group of P. Okay. Hence, there is a line bundle LP lambda on the full on G mod P. And in particular, it can be restricted to this Schubert variety. Okay. So let's consider the following diagram. We have the global sections of the guy in question with coefficients in our line bundle, and there is the restriction to global sections of the Schubert variety in question with coefficients in its pullback, L of lambda. Okay. Now we can restrict sections from the ambient partial flag variety. And here we can restrict sections from the ambient full flag variety. Okay, and also we have this pullback. So this pullback is sort of pi bar upper star, and this pullback is pi upper star. Okay. Yeah, very good idea. And what do we know? We know that this is just a restriction from partial flag variety to the Schubert variety. And this is surjective, right? This restriction from the full flag variety to some Schubert variety, this is also surjective. Okay. Now, this is the pullback from line bundle on G mod P to B, but it is an isomorphism altogether because this line bundle descends and the fibers are just P1s. Yeah, the map from B to G mod P is P1 fibration, and there are no on any fiber, the global sections are just constants. Yeah? Fine, but this implies that such a map is necessarily surjective. Okay? It's necessarily surjective, but then it implies that it is an isomorphism. Yeah, because what else could happen? It might have a kernel, right? But you know that this map is birational. So if a section if some section lies in the kernel, it vanishes, then it must vanish on this open set where it's an isomorphism. Then it must vanish everywhere at all, right? So on the dense open subset, there's an isomorphism, so it cannot possibly have a kernel. Pi bar birational. Okay, but then we're in this situation of lemma 7b, and we're done. Uh, 7b. Okay. Yeah, very good. But now probably I'll have to erase. Maybe I'll erase this statement, normality. So again, it's a very elegant proof of normality, but it's very, very important. And you see that it's hard, difficult. I mean, today we only applied all the previous hard work, but it does depend on all the previous hard work. Okay, without Frobenius splitting, we would not be able to deduce this. Okay, so now the next theorem, 10, says that for any parabolic subgroup P and any Schubert variety, the projection pi, well, it goes from the ambient flag variety to G mod P, but inside we have XW, and it goes to the parabolic version of XW. So, well, again, it will be denoted pi, and it is rational. So the full direct image of structure sheaf here is a structure sheaf here. For example, from the flag variety from a full flag variety to the parabolic flag variety. Okay, so this is rational, first of all. It implies, as we know, that for any locally free vector, sheaf S on the parabolic Schubert variety, its cohomology on the parabolic Schubert variety are the same as its cohomology with pullback on the full Schubert variety. Okay, and also the second claim is that for a reduced decomposition, of W into the product of simple reflections, the de Mazur resolution is also rational. And again, this implies the same thing, that for any vector bundle, the pullback with respect to de Mazur resolution from cohomology on the Schubert variety is an isomorphism to the cohomology of de Mazur resolution with coefficients in the pullback of this vector bundle. Okay. Yes. Yes. No. In general, absolutely no. No. So maybe terminology sucks. Yeah, that's what you. Yeah. So the terminology sucks at this point. There are two different notions of rational morphism. I apologize. Yeah, but today we only work with one. So in general, rational means that it's not everywhere defined. It's only densely defined. Yeah, and today it means something different. So in general, no. In general, resolution, I mean, blow up will not be. If you blow up something smooth, then it will be rational. But if you blow up something singular, if it's singular enough, then it will not be not rational. For example, exactly, yeah. To take any plane curve and take a cone over this curve. Some surface with singularity at the vertex. Oh, how did it? Something like this, yeah? And then blow up this point. And you will glue in this very curve. But this very curve does have higher cohomology, and they will appear. Yes. For normalization, already zero direct image fails. You don't need even higher direct images. Non-normal variety does not have rational singularities by the very non-normality. Well, all the Schubert varieties have rational singularities. All the de Mazur resolutions are rational morphisms. Well, rational singularities are very good and very rare in nature. But all the singularities we acquire for Schubert varieties, they are, in this sense, very good. Well, for example, what we just observed in this example, when you take de Mazur resolutions, all the fibers over singularities, so general fibers are just points, they're resolutions. But at the singularities, they acquire some bigger fibers, but all those fibers have cell decomposition. Yeah, in scientific language, you would say they're Tate motifs. But in general, absolutely nothing like this happens. Usually when you resolve singularities, you acquire some, higher genus curves or, non-Tate motifs. So the general fibers will not have cell decomposition. Yeah? It's a very specific situation that the singular fibers have cell decomposition. It always happens for Schubert varieties, but essentially never more. But then it's just non-normal and it doesn't work again. Yeah. But even if we stick to normal varieties, still in general, they will not have rational singularities. Okay. So we are trying to prove theorem 10. And let me erase this nice argument, though we'll use it I don't know. Well, let me erase it. Maybe you'll remember it for a couple of minutes. Okay. Proof. For any dominant lambda, the weight of parabolic subgroup, the pullback morphism from global sections on the parabolic Schubert variety of this line bundle surject onto global sections on the full Schubert variety. So just as what I erased. Okay, the same argument. And again, the same argument implies that this pullback is an isomorphism. Okay. And then by theorem 8a, it implies that the higher cohomology of the Schubert variety with coefficients in this line bundle vanish. So theorem 8 was just the direct consequence of compatible Schubert splittings. Yeah. Well, if I formulated it half an hour ago, since everything is compatibly Frobenius split, all the higher cohomology of dominant line bundles vanish. But then it implies by this miraculous lemma 7 and also 6, some trivial lemma, it implies what we wanted to prove. Okay, the rationality of this pi. Okay. And similarly for de Mazur resolutions. So this will be induction in the length of W. What was it? Capital N. So we set, we take subsequence R is just SI2, so on, SIN. So I just forget the first simple reflection, and we take V is this product, SI2 times so on times SIN. So we have W is SI1 times V. Okay, and then our de Mazur resolution is the composition of just by construction, by definition, the parabolic PPI1, the product maybe under B with theta R from P I1 product under B with ZR into P I1 product XV into XW. Say this is F Didn't we discuss it? It is the quotient model diagonal action of B. It acts on P on the right, on Z on the left, and then we take quotient model diagonal action. It is discussed with Vanya. Yeah, sorry. Okay, what shall I erase? Maybe now I finally erase my favorite lemma 7. Okay, so by our induction assumption, theta r is rational. And then when we take this composition, so this is just P1 bundle. P1 bundle is rational, so the composition is rational as well. So Pi1 product under B theta r is rational as well. This F, this just the action. Just the action morphism, but it's somehow it's how to say. When we defined our de Mazur resolution, it was constructed recursively from such morphisms. It's somehow, so to say, partial de Mazur resolution. It had length n. This smaller Schubert variety has length n minus 1. Then we can apply similar procedure to n minus 2 and so on. And when we reach the end, we just obtain the full de Mazur resolution. Okay, so this is rational. And now F is rational since xw is normal. And by the next claim, I will formulate this claim immediately, and plus lemma 6 about composition of rational morphisms implies B. Okay, so I only promised some claim. Here is the claim. It's proposition 7, and it says that in our situation, when W is SV, and we take this subminimal parabolic, P equals B and BSB, then the fibers of this partial resolution are connected, and the first, well, in fact, all the higher direct images vanish, and hence F is rational. Okay, so in the previous proof we had this map of interest. We decomposed it into composition of this partial de Mazur resolution F and something we knew by induction assumption. So we only needed to know that f is rational. Then the composition with f would be rational too. So now the next proposition 7 claims that f is rational, and that's what we have to prove now. So logically we're still in the process of proving theorem 10, which I'm erasing. So we're still proving that the de Mazur resolution is rational. Okay, so there we are. Well, in fact, we know that W is SV, and it's longer, but in this proposition, it's not necessary. We can also prove it for the case when W is shorter than V. Then it's an easy case. So if SV is less than V, then P xv will be just xv, and this product under B will be just the direct product P mod B times xv, and well, it's just P1 times xv, and the projection will be just this projection, and it's clearly rational, just because the zeroth cohomology of P1 is constants, and higher cohomology is nothing. So this is an easy case. So the interesting case we are working with is SV is bigger than V, and then P times xv is xw, and take any point, small x, in this bigger Schubert variety. Then the fiber, we want to prove that the fibers are connected. The fiber over this point is the set of parabolic elements such that P inverse x lies in xv modulo Borel subgroup. So the action of Borel is P times B is just the product P B. Okay, and this implies that this fiber is a subscheme of P mod B. That is projective line. Now, since P acts on this thing and everything is P equivariant, we can choose our x as we please in the orbit of P. So we can choose x any point in the P orbit, and we will choose it. Well, I never said it aloud, but maybe everybody heard it somehow, that there's a maximal torus action on the flag variety, and there are just finitely many torus fixed points, and they are numbered by the Weil group, and they are sort of centers of the Schubert cells. So each Schubert cell, CW, has a unique T fixed point, what is usually denoted W, like this. Okay, so we can take for X such a point that will be torus equivariant, torus invariant, sorry. And then the usefulness of such a choice is in the fact that the torus will act on this fiber. Yeah, just the whole set, the fixed point set of the torus is just W. And namely, any cell contains a unique torus fixed point. Okay, like in P1. That's the case we'll consider right now. There are just two torus fixed points, 0 and infinity. The torus is just X by dilations on P1. Okay. So if X is T invariant, well, T fixed, so let's say, then T acts on the fiber and well, this fiber inside, sorry, P mod B is T invariant. Okay, but now there is not a large supply of T invariant subvarieties in P1. Yeah, and the only so what we are trying to prove is that the fibers are connected, right? And can you imagine any disconnected torus invariant subvariety of P1? Any at all? Hmm? If you stretch your imagination to the utmost extent, what can you imagine? Lёня. Сергей. Шуай-шуай. Ваня. Disconnected torus invariant subvariety of projective line. It's connected. Right, absolutely. The only invariant, sorry, the only variant, the only T invariant disconnected subscheme of P1 is, well, must be supported at 0 and infinity. Okay? Otherwise, it's necessarily connected. You cannot imagine anything else. Okay. So, well, we can choose X, because it's in P orbit, we can choose it in such a way that X is smaller than Sx, and then smaller W, because it's in the closure of, it's in this Schubert variety, it contains only points smaller than W. Okay, and well, this will be just B, and this will be SB in invariant terms. And since we know that x is smaller than Sx, this implies that x inverse of the simple root alpha, well, we have this Si, well, alpha I is negative alpha I, so it's reflection in this simple root. Well, alpha I if you want, I don't know. So x inverse of alpha is positive, and this means that S times U alpha x lies inside x v, and it means that the fiber contains U alpha S B, and this is the whole affine line. So it's a contradiction. Okay, so the fiber is necessarily connected. We proved this part. And now we have to compute the higher direct image. So we know that the dimension of all fibers is at most 1, because they are all contained in P1. Okay, and hence the higher direct images with degree bigger than 1 necessarily vanish. We only have to check the first one. Yeah. So let's try to compute the first direct image. Okay, so F is the composition of a closed embedding, P product under B with XV, embeds, say, I don't know how to say it, S, no, S is also bad, sigma, sigma to P mod B, which is P1 times XW, and then just projects to XW. And here sigma of Px modulo B is just P times B, P times X. So the first direct image of the structure sheaf P with X V is the first direct image of this projection of the direct image under this closed embedding. It only has the zero direct image. It's a closed embedding, right? It doesn't have higher direct images. So if you want this spectral sequence, Leray spectral sequence, but in the most trivial case. Okay, so the structure sheaf of our PXV. But here the first direct image vanishes just because this projection with fibers P1 and PP1 has no higher cohomology of structure sheaf. Okay. So there we are. but maybe let me. Pardon me? Then it implies that the zeroth direct image is the structure sheaf. Right? Like, well, when you resolve the nodal singularity, there will be two points in the fiber, and the structure sheaf the direct image of the structure sheaf will be bigger. In this situation, the the zero direct image of the structure sheaf will be the structure sheaf. There are potential problems with higher direct images, but the zero direct image is just the structure sheaf. Maybe let me explain it just a little bit. Let me add two words about this. So we have surjection from the structure sheaf of this thing, P, B, X, V, onto the structure sheaf of the direct image. Sorry, here we have P1 times X W, and here is a closed embedding, so there is the structure direct image of the structure sheaf of this embedded variety. Okay, this is an embedding, this is a projection. Here?
Yes,
here? Well, it's just okay. P mod B times XW. Okay, there's surjection. It's a closed subvariety. Sigma is a closed embedding, so it's a closed subvariety of such a surjection. Okay? We know that the second direct image vanishes, and hence this implies the surjection on the level of first direct images. Sorry. Okay. But this is zero. So this is zero for this reason. Pi was just projection. And on this factor, this will be zero. So hence, this is also zero. Okay, and we are done with this. And the time is up. But the next time, what did we prove? We proved that the de Mazur resolutions and the projections from Schubert varieties in the full flags to partial flags, they are all rational morphisms. So they have no higher direct images, and the zero direct image of the structure sheaf upstairs is the structure sheaf downstairs. That's what we proved. And next time from this we will derive the de Mazur character formula and the Weil character formula. So now we are almost at the end of our enterprise. Next time we will derive the character formulas from this knowledge. Absolutely, yes, yes. Mm-hmm.